Hello, my fine feathered fiends. As promised, we're continuing 3.4. This is part 3 of our 3.4 treatment. I'm going to say treatment, I like that word. And we're going to do this is U substitution, but U substitution with limits of integration on the problem. In other words, we have the 0 and the 1 over there. And that's going to just make things there's going to be a tiny tweak we're going to need to do. But let's start by doing the U substitution itself. So we're going to I'm going to let U equal 3x minus 4. U is going to equal 3x minus, I'm sorry, 3x minus 1. And du is equal to 3x, is equal to 3 dx, which means 1/3 du equals dx. Okay, now I'm gonna, this is just now gonna be the integral of u to the 4th, because this here, that's just u, right, to the 4th, and dx is 1/3 du, so it's du, and I'll put the 1/3 outside. Okay, now notice, did you all notice that I didn't write the 0 or the 1? At least not yet. Why didn't I not? What am I waiting for? What's the holdup? Well, here's the thing. You see, this is x is going from 0 to 1. This is the integral as x goes from 0 to 1. But it's no longer an x integral. Now it's a u integral. So what I have to do is, just like I translated the x into a u, I have to translate these parameters to fit u. In other words, when x goes from 0 to 1, what's happening to u? Well, if x is 0, u is 3 times 0 minus 1. And if x is 1, u is 3 times 1 minus 1, which is equal to, of course, that's 0, that's just -1, and that's 2. So I'm going to make the integral from -1 to 2. You see, I had to change the limits of integration. You need to change the limits of integration. And now that I've done that, let's continue. This is, excuse me, this is 1/3. This is 1/3 u to the 5th over 5, because that is the antiderivative, evaluated between -1 and 2. This is going to be 1/3 times 2 to the 5th over 5 minus -1 to the 5th over 5. And that's going to equal, let's see, 1/3 times 32 fifths, plus, looks like plus 1/5, which is going to be, let's see, 1/3 times 33 fifths, which is going to equal 11 fifths. And that's my final answer, 11 fifths. Now, I want to show you, we could have done this problem a somewhat different way, and it also works. And again, I'm going to show you a second way, a second method that you could have done. We could do. Both are correct. And you know, let's going to call this method. So we'll call this method 1, like method acting. Now we're going to do method 2. So we're going to look at so again, let's just start from the beginning. We're going to go the integral from 0 to 1 of 3x minus 1 to the 4th dx. And we're going to let u equal 3x minus 1, and du equals 3 dx, which means 1/3 du equals dx. And same old. And this becomes the integral of u to the fourth times 1/3 du, which is equal to 1/3 u to the fifth over 5. Now notice I haven't written any numbers here. So what I'm going to do at this point is I'm going to back substitute. This is equal to 1/15th. We'll say 1/15th. Times, now we're going to back substitute 3x minus 1 to the fifth. And now we're going to evaluate. Now, since I've gone, since I was in U territory, where there was 0 and 1 were not good. But now I went back to X territory, and now the 0, 1 are good again because I'm dealing with X's. So I'm going to go between 0 and 1. And this is going to equal 1/15th times 2 to the fifth power minus 0. So we're just saying 2 to the fifth power, which is equal to, hold on a second. My bad. I just realized I missed something up here. Something doesn't make sense. I'm sorry, sorry about that, minus 1/15th times, well, that's 3 times 0 minus 1. That's -1 to the fifth. This whole thing becomes 1/15th of 32 plus 1/15th, which equals 33/15ths, which equals 11 over 5. Same answer, exact same answer we got before. See, before we got 11 over 5, now we got 11 over 5. Exact same thing. So you have two choices now. You can keep it in U and change the limits of integration, or you could back substitute back to the X and use the original limits of integration. And when I said before, these are the tweaks, so minor tweaks have to be done. That's it. That's the tweaks I was talking about. You have to deal with the limits of integration, and I just showed you two ways how to do it. So let's celebrate this newfound knowledge with another problem. Let's do the integral. Let's do the integral of from 2 to 10 of ln x to the sixth power over x. So I'm going to let u equal ln x. Du is going to equal dx over x, which is very convenient because I have a dx over x right there, which, by the way, that's actually what I noticed. I noticed that when I started. I didn't say anything about it, but I noticed that at the outset, and that's what motivated me to use U substitution in the beginning. I mean, altogether. So this becomes the integral. Let's see. I'm gonna do the back substituting thing here. So this is going to become the integral of u to the sixth du, which is u to the seventh over 7, which now is equal to ln x to the seventh over 7, evaluated between 2 and 10. So it's just ln 10 to the seventh power over 7 minus ln 2 to the seventh power over 7. And this is approximately 49. Approximately 49. I'm really more interested in, for now, I'm really more interested in that the exact answer. Anyway, that's a nice example. Let's do another one. But again, what I did here is instead of changing the limits, instead of adapting the new limits, because I could have adapted these limits and stayed with U and never bothered going back to the back substitution, or I could, 6 of one, half dozen of another. It's whatever you feel more comfortable with at the time. Here's a fun problem. Now I want to say something. I can tell you right now, just by looking at this, that the answer is going to be 0. Um, and the reason is because when this here is what we call an odd function. Meaning that this is going to be, how do I say it? The graph is going to look something. If I would graph this, I'm not going to do the precise graph, but if I would graph this, it would be something like whatever I have here, I'm going to have the same thing there. So this here is going to be the negative area of that there. So I'm guaranteeing this is going to wind up being 0. I'm not saying that's the graph. I'm just saying whatever the graph is. So, but let's go through it. Let's go through it and let's figure this out. And let's show definitively. I'm just saying, I think it's going to be 0, but what do I know? Maybe I'm wrong. Let's actually crunch it out. So I noticed that the derivative of x squared is 2x. So I'm going to let u equal 1 plus x squared, and du is equal to 2x dx, which is perfect because I have that, I have that right here, 2x dx. So this now is equal to the integral. And the integral, let's just say that, of du over u. The integral of du over u. I'm over you. I get it. It's never mind. And let's since the last one I did with back substituting, this one I'm going to do with changing the parameters. So if let's see, if x goes from -2 to +2, then u is going to go from, oh boy, look at this. U is going to go from 1 plus -2 squared to 1 plus +2 squared. So u, which is, of course, that's 5, and that's 5. Now, I can tell you right now, we already learned that if an integral just goes from 5 to 5, it means we're just looking at a straight line, right? Again, well, there's nothing to talk about. Anyway, this is just going to be, let's just follow this through. There's going to be ln, excuse me, this is going to be ln 5. Ln u, I'm sorry, ln u, a value between 5 and 5, which is equal to ln 5 minus ln 5, which is equal to big fat 0. So we saw this 5 ways from Sunday. That this is, I saw right away, I recognized the negative to the positive of an odd function. It would be, here I recognize that I'm going from point to itself, because this basically means I'm looking at the graph of y equals 1 over u, which looks like that, but I'm just looking at that line, that's 5. So I'm just looking at the area inside the straight line. That's a 0 area. It's, a straight line is an infinitely thin, thing. So anyway, either way, so whether we looked at it based on some logic, common sense, or numerically, we see we got nice answer of 0. And isn't that nice? 0 is a very nice round number. Anyway, everybody, that concludes part 3. I hope you've had as much fun and excitement and thrill as I have. And we'll see you guys next time. Bye.